So, when you're dealing with distributed transactions, achieving consensus can be a real headache. I mean, Paxos is theoretically sound, but it's just so cumbersome to implement in a production environment.
Yeah, I've seen how complex the state transitions get. It feels like we're constantly chasing edge cases.
Absolutely. And then there's Raft. Much simpler to understand and implement, but it still has its quirks. Like handling network partitions without sacrificing consistency or availability. You know, that cap theorem stuff.
Right, especially when you have to ensure all nodes agree on the same sequence of events. It's almost poetic how each algorithm tries to solve the problem differently.
Poetic. More like a nightmare sometimes. Have you ever tried debugging a system where different parts are running under different versions of these algorithms? It's like trying to find a needle in a haystack while blindfolded.
True, especially when logs start getting inconsistent across nodes. It's hard to pinpoint what went wrong.
Exactly. And don't even get me started on how some teams try to roll their own solutions instead of using well-established algorithms. They think they can do better, but end up with something that works most of the time, except for those critical moments when it fails spectacularly.
That happens often enough. The trade-offs between simplicity and robustness are tough to balance.
Tough indeed. Sometimes I wonder if we'll ever reach a point where we won't need to worry about these issues anymore. But until then, it's back to the drawing board every time something breaks down.
Definitely feels like an endless cycle at times.
Oh, absolutely. But hey, at least we get to keep our job solving these puzzles day after day. Who knows, maybe someday, someone will crack the code and make distributed systems as simple as local ones.
Wouldn't that be something? Until then, though, we're stuck with this fascinating yet frustrating challenge.
Speaking of distributed systems, let's talk about the two-phase commit protocol. It's been around for ages and is still widely used, but it has some serious limitations.
True, especially with blocking issues when coordinators fail. It can really bring everything to a halt.
Exactly. When the coordinator goes down, you end up with transactions hanging indefinitely. And if you have multiple coordinators, things get even more complicated because you need to ensure they all agree on the same state.
Right? And the performance overhead from all those round trips can be significant too.
Absolutely. Plus, there's the issue of scalability. As the number of participants grows, the time and complexity involved in coordinating everyone increases exponentially. It becomes a bottleneck pretty quickly.
Not to mention the risk of deadlocks when you have multiple nested transactions.
Yes, exactly. And then there's the problem of partial failures, when some nodes succeed and others fail, leaving your data in an inconsistent state unless you have robust recovery mechanisms in place.
Which isn't always easy to achieve, especially in large-scale distributed environments.
True. That's why many modern systems opt for alternative approaches like consensus algorithms or eventual consistency models that trade strong consistency guarantees for better fault tolerance and performance.
Makes sense. Those alternatives seem to handle real-world complexities much better.
Definitely. Although it's worth noting that, while two-phase commit might not be perfect, it does provide strong consistency guarantees which are crucial for certain types of applications where any inconsistency could cause big problems.
Agreed. There's no one-size-fits-all solution here.
No, indeed. Each approach comes with its own set of trade-offs, and understanding those is key to making informed decisions about what works best in different scenarios. Speaking of handling inconsistencies and failures, have you looked into compensating transactions lately? They can be a lifesaver for recovery in distributed systems.
Yeah, they do seem like a practical way to roll back changes when something goes wrong. But they add another layer of complexity.
Absolutely. With compensating transactions, you need to design your system to not only perform the initial actions, but also to know how to undo them properly. It's like having a reverse gear for every forward move.
That does sound intricate. How do you ensure that the compensations themselves don't fail?
Good question. One approach is to make sure that compensation actions are idempotent. That is, they produce the same outcome no matter how many times they're executed. This helps prevent cascading failures if something goes awry during rollback.
Idempotence certainly simplifies things. What about tracking all the necessary steps for compensation?
Well, you typically need a robust logging mechanism to keep track of all the operations and their corresponding compensations. That way, if something fails, you can replay the logs and apply the compensating actions accordingly.
Tracking everything sounds crucial then.
It definitely is. And let's not forget about timing issues. If a transaction takes a long time to complete, ensuring that the compensating actions are triggered correctly can become quite tricky.
Especially with distributed systems where network delays and node outages are common.
Exactly. You need to account for those delays and make sure your system can handle retries and timeouts gracefully. Otherwise, you might end up in an inconsistent state again.
Handling all these edge cases must be challenging.
It is indeed. But with careful planning and thorough testing, compensating transactions can significantly improve failure recovery in distributed systems. Speaking of distributed systems, let's shift gears a bit and talk about managing transactions across microservices architectures. It's another beast altogether.
Absolutely. Coordinating transactions between multiple services can be incredibly complex.
Indeed, each service operates independently, and ensuring that all of them complete successfully or roll back together is quite a challenge. Synchronous calls can help, but they introduce latency and coupling.
And asynchronous communication adds another layer of complexity with eventual consistency.
Exactly. That's why patterns like Saga come into play. By breaking down a transaction into smaller, manageable steps, each handled by individual services, you can maintain some level of control over the overall process.
Sagas sound promising, but implementing them correctly seems daunting.
It certainly is. You need to define compensation actions for each step, so that if something fails, you can unwind the transaction reliably. It requires meticulous planning and coordination among the services.
Managing those compensations must be tricky.
Very much so. You also have to consider how to propagate the context across services. Distributed tracing tools can help here, but setting them up properly is non-trivial.
Tracing definitely aids in debugging, but doesn't eliminate the core complexity.
True. Another approach is using transaction managers that support XA transactions or similar protocols designed for distributed environments. They handle the coordination and ensure atomicity across different resources.
But those traditional methods might not fit well with modern microservices architectures due to their synchronous nature and overhead.
Correct. Modern solutions often lean towards event-driven architectures, where each service listens to events produced by others and acts accordingly. This decouples the services while still allowing coordinated behavior through event streams.
Event sourcing combined with CQRs could work well there.
Absolutely. Combining these patterns allows you to scale horizontally and manage transactions effectively without tight coupling between services.